This is lesson 76 on counters. Here's a state diagram for a 3-bit divide by 8 counter. Each circle here represents a state. We've labeled the states S0, S1, S2, 3, 4, 5, 6, 7. And in the circle we've shown the output of the counter in each state. So in state S0 the output will be 0, 0, 0. Then on the next rising edge of the clock the state will change to 1, then to 2, 3, 4, 5, 6, 7, and back to 0. So this is a 3-bit counter which is going to count from 0 to 7 and then repeat itself. Let's see how we can design such a circuit. We need 3 flip-flops because we have 3 bits, Q2, Q1, Q0. So we'll have a flip-flop for each bit. Each one will have an input D, D0, D1, D2. And here's the truth table for the counter. We've listed the 7 states, S0 to S7, and then we've shown the present state. The present state is indicated by the outputs of the flip-flops. So Q2, Q1, Q0 is going to start in state 0, 0, 0. So we'll have a 0, 0, 0. Now on the next rising edge of the clock, we want this to change to 1. We want the outputs to change to 1. But you remember how the D flip-flops work. On the rising edge of the clock, whatever's at D gets latched to Q. So all we have to do is line up a 1, a 0, 0, 1. If we line a 0, 0, 1 in the 3 Ds, then on the next rising edge of the clock, that 0, 0, 1 will show up at the Qs, and we'll have 0, 0, 1. We're in state 1, we want to go to 2, so all we do is line up the 2 on the Ds, 0, 1, 0. Next rising edge of the clock it goes to 2, and so forth. To go to 3, we line up a 3. To go to 4, we line up a 4. To go to 5, we line up a 5. To go to 6, we line up a 6. Go to 7, we line up a 7. And when we're in state 7, so the output's 1, 1, 1, we want to line up 0, 0, 0, so we go back to 0. So here's the truth table. So what do we have to do? Well, we have to add some combinational logic out here to produce D0, D1, D2 in order to make this a counter. Well, we can use this truth table. We can think of the input to the combinational logic circuit that we're going to put out here as being Q2, Q1, Q0. In other words, we're going to take Q2, Q1, Q0 and feed them back as inputs to this combinational logic circuit whose output will be D2, D1, D0. Well, we know how to find the logic equations for D2, D1, D0. We can just use Carnot maps. So let's try it. Let's look at D2. We got a min term 3. So we put a 1 here. We have a 4, a 5, and a 6. So how many circles do we have? Well, we wrap this one around. We can't do anything with this one. And we have a circle here. So we can just write the logic equation for D. This would just be the min term, not Q2 and Q1 and Q0. This circle is going to give us what? So we'll have or Q2 and not Q1. And the wraparound will be Q2 and not Q0. So here's the logic equation for D2. And we can do the same thing for D1. We have a min term 1, min term 2, min term 5, and min term 6. So 2 circles here, circle here, circle here. What's the logic equation? D1 is going to be not Q1 and Q0, or Q1 and not Q0. So there's a logic equation for D1. And then we can find the logic equation for D0. We have min term 0, min term 2, min term 4, and min term 6. How many circles here? Yeah, just 1. Remember, it wraps around. So what do we have? We're only left with not Q0. So D0 is not Q0. So we have the 3 logic equations, and we can just draw the full circuit for the divide by 8 counter here. the outputs will be Q2, Q1, Q0, and here's the logic equation. You see D0 is just not Q0 that we got from the Carnot map. Q1 is just going to be D1. Here we're looking for D1 is just going to be Q1 and not Q0, or Q0 and not Q1. And similarly, here we had the 3 AND gates. So this circuit will produce a 3-bit counter. When we have a clear signal not shown here, it will clear to 0, 0, 0. And then on every rising edge of the clock, this output will count from 0, 0, 0 to 0, 0, 1, and then to 2, 3, 4, 5, 6, 7, and then back to 0, 0, 0. So we've designed a 3-bit divide by 8 counter. We'll see in the next lesson why we call it a divide by 8 counter.